Hello everyone, Mr. John here from Areteem Institute. In this week's Thursday Tidbit, we're going to be talking about the principle of inclusion-exclusion. Now, inclusion-exclusion is a trick for helping us count things when we might have overlaps between groups. Little bit of notation. When we're doing math, we typically talk about groups as sets. So instead of one group and a second group, we say a first set and a second set. We use n to denote the size of these things. So if we have a set of squares and a set of rectangles, we could ask how big is the first set, how big is the second set with this n. Now, in terms of these overlaps, we have this idea of the union and the intersection. Now, these things are a little bit easier than they may seem at first glance, and we're only going to use them just for helping write out the formula and making it a little bit easier to read. So A union B, we can read as basically the word or. A union B is everything that's in A or in B or in both. So this is everything in one or the other group that we're counting. The intersection is the AND statement. So this is exactly the overlap between the two sets. So union is or, one or the other, or both, and the intersection is exactly both of these sets. And the reason we're going to be looking at these is then they're actually very related to each other when we're talking about counting the sizes of these sets. Now, what is the natural question we might want to answer? Well, given two sets, right, we want to know how big the union is, right? And this is a natural question because you might draw out our two circles here are going to denote our two sets. So we have A, we have B. You might know how big they are separately, right? You have some number of squares and some number of rectangles drawn out on a piece of paper. Well, maybe some of them are the same, right? We might have some of this overlap in the middle that we want to be worried about. So if we're trying to count the union, so this is everything in A or B or both, right? So remember this union here is everything that's going to show up somewhere in these two circles here. So how can we go about counting this in a kind of systematic way? Well, we can start by counting everything in A. So I'm just going to use tally marks here to denote we've counted the things in A and, right, possibly they're in the overlap too. And here's where we kind of start to notice an issue that can arise. When we start counting the things in B, well, that's going to count everything over here, but it's also going to count everything in the middle again. Now notice we've counted the stuff in the middle twice. But wait a second, that middle is exactly the intersection. So if we highlight this portion here, that's exactly the intersection. So if we subtract it off, right, that is we get rid of one of these pieces there. Now we've counted everything once. So we counted everything in A, we counted everything in B, and we've counted everything in the overlap once because we had to subtract it off there. And this systematic way of adding up each set separately, then subtracting the overlap, that's really inclusion-exclusion. And this is really more powerful the more sets we have. So let's look at the formula for 3 sets. And this looks pretty complicated, but if you think about it in the same kind of pattern, it starts to make sense. So we start by adding up the 3 sets themselves. So again, you just look at the first set, how big is it, second set, third set. Then you subtract off the doubles. So we subtract off the overlap between each pair of sets. How does A and B overlap, A and C overlap, B and C overlap? Now, With 3 sets, we actually have a problem. You're actually subtracting off too much, so we have to add back in the intersection or the overlap of all 3 of the sets there. We're going to see this with an example here in a second, but I just want to point out too that this can be expanded for any number of sets. So I recommend you draw the picture for 3 sets, try to do the tally marks like I did to really understand this formula. And just know that if you need to use it for a larger number of sets, you can as well. Okay, let's look at the standard example of inclusion-exclusion. So suppose we have the numbers 1 to 100. So 1, 2, 3, up to 100, right? 100 is included. 1 could possibly be included. And we want to know the number of these that are multiples of at least one of 2, 3, or 5. Right, so this is a pretty standard question for inclusion-exclusion. And once we start writing it out, it should be fairly clear why. Right, so if we just start thinking about these in terms of sets, well, maybe A is all of the multiples of 2. Well, it should be pretty easy to list out all the multiples of 2, right? We just have all of the even numbers. 2, 4, 6, 8, 10, blah, 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 all the way up to 100. And then how many of these are there, right? We can turn this into the size of A. Well, it's every 2 of them, so there are 50 of these in total, right? A has size 50. And it should be pretty clear that we can do the same type of stuff for B and C, right? So this is going to be pretty easy to do the same way there, right? C could be all the multiples of 6, so 3, 6, 9, all the way up to, be a little careful here, this only goes up to 99 in this case. And so now the size of B is actually 33. And we have the same stuff for C. Now all multiples of 10. So 5, 10, 15. This one goes all the way up to 100. And for this one, there are 20 elements that we're going to be worried about there. Well, just from our picture now, we start to see some issues. We start to see some problems. The number 6 is counted in the first list and the second list. The number 10 is counted in the first list and the third list. Right, so we have these overlaps. We're definitely overcounting things. And this is exactly where inclusion-exclusion comes into play. So how about we consider their intersections? So what does it mean to be a multiple of 2 and a multiple of 3? Or a multiple of 2 and a multiple of 5? Right? These things are actually easy. If you're a multiple of 2 and a multiple of 3, well, you're a multiple of 6. So here we have 6, 12, 18, right, up to the last multiple of 6, 96 in this case. Right, so you can use the same type of strategy here for counting the size of these intersections. 6 times 16 is 96, so this here is going to be 16 multiples of 2 and 3. Multiples of 2 and 5 are multiples of 10. So this is 10, 20, all the way up to 100. It's pretty easy to see in this case we have 10 of these. So the size of the intersection of A intersect C is 10. Multiples of 3 and 5 are multiples of 15. So 15, 30, all the way up to 90. And there are 6 of them in this case. So B intersects C is equal to 6 here. Now, how do we kind of finish this? Do not forget the 3 set possibilities, right? So we have the possibility of A and B and C. So these now are a little bit harder to visualize in terms of kind of why we add or subtract this. But if it's a multiple of 2 and 3 and 5, well, it's actually a multiple of 30. So there's only 3 of these that we have to worry about from there. So we have 30, 60, and 90. There are 3 of these in this case. So intersecting all 3 of these things gives us 3 elements that we have to worry about there. Now, putting this all together towards a final answer, right? Remember, I color-coded these kind of for a reason here. We start by adding the numbers together, right? So if we are worried about our final answer here, we start by adding the numbers, 50 plus 33 plus 20. So the first 3 numbers are added. The next set are all subtracted. So minus 16, minus 10, minus 6. And finally, we add stuff back in. So plus 3 at the end. And this is going to give us a final answer. I'll let you double check my calculation there of 74. So once we have all of the pieces, we remember, add the singles, subtract the doubles, and add back in the triple. And this gives us our final answer of 74 multiples of 2, 3, or 5 in this case. Now, this question was a good example, remember I mentioned, of counting and probability. So if you want to learn more and much more kind of about counting, how you organize your counting thoughts, how you can turn these into probability and chance, our online summer camp this summer will be a great thing to join. You can join all 4 sessions in July, or if you're specifically interested in counting and probability, it's from July 19th to the 23rd. This is open for middle school and high school students. Hopefully, I will see you there. As usual, check back each Thursday for a new math tidbit. If you want to practice daily, check out ziml.areteem.org for our Zoom International Math League. Otherwise, like and subscribe if you enjoyed this video, and I will see you guys all next week. Goodbye.